Welcome to podcast number 1 of lecture 2 for chapter 13, Alkanes and Radicals. This is a slide showing a volcano in Mexico, pretty neat photo, mountaintop above the clouds. The next slide has a quotation, all truth is God's truth, truth that is both revealed and discovered. And of course, we can learn about God's truth that's revealed in the Bible, and we can learn about God's truth that we can discover through science. Okay, we're going to talk about formation of explosive peroxides. Ethers can form explosive peroxides when concentrations are above 100 parts per million by reacting with oxygen when exposed to air. And on the next slide, we're going to look at the mechanism. And of course, exposure to air, we're talking about heat, light, and oxygen. A peroxide compound contains an oxygen-oxygen bond, which is easily cleaved, resulting in a radical that can create new radicals, which can be an explosive situation. Therefore, a peroxide is a radical initiator. Ethers contain a stabilizer like BHT, that I'll talk about a little more in just a minute, or actually ethanol can be a stabilizer that traps the chain initiating radical, preventing the formation of explosive peroxides, as we'll see in the mechanism in a second. But BHT is butylated hydroxytoluene. It scavenges the free radical species, and the structure is a benzene ring with a methyl group. Of course, that's toluene, and butylated gives us the idea that there's butyl groups, but there's actually two butyl groups on the benzene ring, and an OH completes the structure on the benzene. So it's butylated hydroxytoluene. If an ether is purified, or in other words, pure ether with no stabilizer, it must be discarded within 24 hours. Of course, that's because of the formation of explosive peroxides. All the ethers that we have in lab are always containing stabilizers. Okay, let's go to the next slide. Here's the mechanism, the formation of explosive peroxides. At the top here, this first reaction, and then you can see the second and then the third, but the first that we're going to hone in on here is a chain initiating radical removes a hydrogen atom from an alpha carbon of an ether. Here's the ether. This Y radical is just a chain initiating radical that's present. It could be a bromine, it could be many different kinds of atoms. And you can see the one barbed arrows indicate the movement of one electron. Of course, this radical is going for the proton, so that's no longer a radical. But when it does that, it leaves a lone electron on the alpha carbon, forming a radical in the initiation step. Now, here we have a radical reacting with oxygen in a propagation state. Now, here's the radical that we just produced from the ether here. Now, it's now a reactant with oxygen, forming a peroxide radical. Notice that this electron pairs up with that electron, forming a bond between the carbon and oxygen, and now we have this structure here where we actually have the radical, the lone electron, the free electron on the oxygen atom, forming a peroxide radical, which is explosive. Then down here you can see we can take the peroxide radical and react it with another molecule of ether. Here's another molecule just like this one up here, with another molecule of the ether in a second propagation step, producing an additional molecule of peroxide, which can actually go back and participate again in this propagation step. Also, we have regenerated the radical used in the first propagation step. This one right here has regenerated this particular radical that was generated up here. So you can see how it's a chain reaction. Okay, let's take a look at this question. Of the following ethers, which one would be least likely to form peroxides, hence be safer to use in a laboratory? Take a look at that for a minute, and then we'll go to the next slide. Okay, here is the answer is E, and just keep in mind, to form a radical from an ether, and of course all of these are ethers, a hydrogen must be removed from an alpha carbon. This must be done before a peroxide can take form. And of course, if you look at all of these, that's an alpha, there's an alpha, there's an alpha. This one's got 2 oxygens, 4 alphas. All of the carbons are alphas. Those are, see, that one's an alpha, that's an alpha. There's an alpha with no hydrogens on it. And there's an alpha carbon with 3 hydrogens. Now, A through D have alphas that have more than 1 hydrogen. All of them have 2 except, I think this one right here is the only one that has 1. E has only 1 alpha carbon with hydrogens, this one. So it would be the least likely to form a radical, which we've got to form in order to form a peroxide radical, where oxygen radical would react with the radical that's formed. Therefore, E is the correct answer. All right, let's shift gears here and look at the addition of radicals to an alkene. The addition of radicals to the alkene. Interestingly, addition of hydrogen bromide in the presence and absence of peroxide yields 2 bromobutane and 1 bromobutane. Addition of HBr to 1 butene results in 2 bromobutane, as we've seen quite a while ago. And this is so because the electrophile, the proton, follows Markovnikov's rule, which is adding to the carbon bonded to the greater number of hydrogens. So it's following Markovnikov's rule. If peroxide is added to the reaction mixture, as in the second reaction, it changes the mechanisms of the reaction. So bromine radical, bromine atom with just 1 electron, the bromine radical is the electrophile. And so it adds to the sp2 carbon with the greater number of hydrogens. So that's why bromine ends up on this carbon, because of the effect of peroxide on the bromine, turning it into an electrophilic bromine radical. Okay, so let's look at the next slide. Here's the mechanism for the addition of HBr to an alkene in the presence of peroxide. The addition of HBr to an alkene in the presence of a peroxide is a radical chain reaction with initiation. Here we go, initiation, propagation, and termination steps, as we'll see on this slide and on the next couple of slides. This shows the initiation steps for the addition of hydrogen bromide to an alkene in the presence of peroxide. The heat or light heterolytically cleaves a peroxide. Here's our peroxide. The R groups, of course, can be any kind of methyl, ethyl, alkyl groups. The alkoxyl radical abstracts a hydrogen from the hydrogen bromide, there it goes, resulting in the formation of a bromide radical. So here's our peroxide forming 2 alkoxy radicals. Notice 1 free electron there. Then, in the presence of HBr, it's going to abstract the proton, forming ROH and the bromine radical. So we've initiated this chain reaction. On this slide, here are the propagation steps for the addition of hydrogen bromide to an alkene in the presence of a peroxide. This is, we'll call this A up here, this is B. in A, the bromide radical, there it is, since it is now acting as the electrophile and so still follows Markovnikov's rule, it will add to the least substituted carbon to form the most stable alkyl radical. In B, the alkyl radical abstracts a hydrogen atom from the hydrogen bromide. As you can see here, there it is, abstracting it. We made it up here, and now we're going to, in the second step here, abstract a hydrogen. So, notice that up here, in the very first step, we have a radical intermediate. Since it's not a carbocation, it will not rearrange. Because of the first species that adds to the alkene as a radical bromine, the addition of HBr in the presence of peroxide is sometimes called radical addition reaction. Radical addition reaction. Here are the termination steps for the addition of hydrogen bromide to an alkene in the presence of peroxide. There are three possible termination reactions. Any two radicals pair up, resulting in the end of a chain reaction. So here's two bromine radicals pairing up, forming molecular bromine, no longer a radical. We have a bromine radical with the alkyl halide radical pairing up. And then we got two of these pairing up, no longer a radical once they pair up and join together. As you would expect from the previous mechanism, the addition of hydrogen bromide to 3-methyl-1-butene in the presence of peroxide yields 1-bromo-3-methylbutane. Notice the bromine, which is going to become electrophilic, goes to the carbon with most hydrogens. And there it is. Because the addition of HBr in the presence of a peroxide forms a radical intermediate rather than a carbocation, the intermediate does not rearrange, as I said a second ago also. A radical intermediate does not rearrange like a carbocation, so that's a good thing. Here is an interesting thing to remember. Notice we've been talking about HBr, hydrogen bromide. There is a difference between the addition of hydrogen chloride, hydrogen iodide to an alkene and the addition of hydrogen bromide to an alkene. Comparing this slide with the previous slides. Here's the addition of hydrogen chloride, hydrogen iodide to an alkene in the presence of peroxide. Both follow Markovnikov's rule. Notice the proton is electrophilic, going to the carbon with most hydrogens in both cases. Now notice that peroxide has no effect on the addition of hydrogen chloride or hydrogen iodide to an alkene. The addition that occurs when a peroxide is present is the same as the addition that occurs when a peroxide is absent. Why is the peroxide effect observed for the addition of HBr but not for the addition of HCl or HI? We call this the peroxide effect. Now the next slide is going to provide the answer. But the peroxide effect, this is when the peroxide makes the bromine radical the electrophile that adds to the sp2 carbon with a greater number of hydrogens. Notice in this example with HCl and HI, the hydrogen is the electrophile, adding to the sp2 carbon with a greater number of hydrogens, not the halogen. But this slide tries to explain this a little bit by looking at the enthalpy calculations. So again, why is the peroxide effect observed for the addition of HBr but not for the addition of hydrogen chloride or hydrogen iodide? The answer lies in looking at the enthalpy calculations for the addition of hydrogen halides to ethene. Now, in the addition of hydrogen chloride and hydrogen iodide to an alkene in the presence of peroxide, one step is exothermic and one step is endothermic. Exothermic, endothermic. In the addition of hydrogen bromide to an alkene in the presence of peroxide, both steps are exothermic. Notice bromine, chlorine, and here's iodide. This results in the difference with the addition of HBr in the presence of peroxide. Notice these are both negative numbers, negative, negative, positive, negative, positive, negative, positive. So that is one explanation. Let's look at a problem before we conclude. Which compound will be the major product of the following radical addition reaction? So here we've got HBr in the presence of peroxide. So let's pause a second and pick your answer. Okay, answer B is correct. Bromine in HBr is made to be electrophilic by the peroxide effect. Of course, peroxide is present, and so it will go for the sp2 carbon that has the most hydrogen atoms by Markovnikov's rule. Notice there's no hydrogens on this sp2. There's one here. Therefore, the bromine is going to go there, forming this product. Okay, that concludes part 1.